Welcome to iLectureOnline. In the previous video, we've made it this far. We've taken this bridge circuit, we took the bottom portion of it, which was a delta, and we converted it into a Y format. We solved for Z1, Z2, and Z3. We then combined that with J4, Z2 with minus J3, and we end up with what we have here in red, the three impedances left, two that are in parallel, and then in series with the third one, which was Z3. For our convenience, I've converted the magnitude, I would say the real and imaginary part, into the magnitude and phase angle format so that we can then use that to calculate the following. We first want to find the impedance of the two impedances in parallel right here. Then we want to combine that to get the total impedance, and then finally we want to get the current through the circuit. So first of all, to get the impedance of the two parallel branches, we take the product over the sum. So the product would be 4.66 with a phase angle of 61.95 degrees, and multiply that times 3.93 with a phase angle of minus 19.5 degrees. And then we divide that by the sum. And for the sum, it's better to leave it in the real and imaginary part. So we have 2.19 plus J 4.11, and add that to 3.7 minus J 1.31. Okay, and that is equal to, for the numerator, we take the product, so that gives us 18.31. So 18.31 with a phase angle of the sum of these two, that gives us 42.45. And in the denominator, when we add these together, so we have that's 5.89 for the real part, and for the imaginary part, plus J, we subtract this from that, so that gives us 3, that's 2.8. 2.8, so 2.8 plus 1.31, that's 3, that's 4.11. That looks like it's correct. Now, of course, to divide the denominator into the numerator, we need to convert this into the magnitude and phase angle format. So this is equal to 18.31 with a phase angle of 42.45 degrees. And now the magnitude of this, that would be 5.89 squared plus 2.8 squared equals, take the square root of that gives us 6.52 with a phase angle of 2.8 divided by 5.89, take the inverse tangent, it gives us 25.43 degrees, 25.43 degrees. And so then when we divide that, we get 18.31 divided by 6.52, that gives us 2.81 with a phase angle of 42.45. We subtract minus 25.43, we get 17.02 degrees. And then if we convert that back into the real and imaginary part, we take the cosine of that angle, multiply times 2.81, and we get 2.69 plus J times, again, 17.02, take the sine of that, and multiply that times 2.81, and we get 0.82. So what we've done now is we have found the impedance of the parallel branch. Now we can go ahead and add that to Z3, which is down here. So that gives us the total impedance. So this is the impedance of the parallel branch plus Z3, which is equal to 2.69 plus J 0.82. And we're going to add that to the impedance Z3, which is 2.02 minus J 1.13. And when we do that, we get the following. Add these two together, we get 4.71, and that would be minus J, and that would be 18, 28, 31, 0.31. So now we have the total impedance, but we have it in the real and imaginary part format. Now we have to convert that into the magnitude and phase angle so we can divide that into our voltage. Our voltage is given right here. So when we do that, this is equal to, magnitude-wise, 4.71 squared plus 0.31 squared. That doesn't change much there. It gives us 44.72 with a phase angle of 0.31 divided by 4.71, and take the inverse tangent. That's 3.77 degrees. That's a negative 3.77 degrees. Okay, now we can go ahead and find the current in the circuit. We take the voltage, which was given to be 45 with the magnitude, with a phase angle of 30 degrees, and divide that by the total impedance, which is 4.72, with an angle of minus 3.77 degrees. And so we get 45 divided by 4.72. That gives us 9.5 with a phase angle of, let's combine that, that would be 33.8 degrees. And of course, that would be in the form of amps. And this would be the current in the circuit after we find the impedance of the bridge circuit, and then we divide that impedance into the voltage to get the current. That's how we do that.